Hello all and welcome to Physics with Pranav. If you're new to my channel, I'm Pranav. I used to be a CAIE student in science and math. I have tutored students from around the world in GCSE and A-level physics, and I am an IGCSE world topper in science from back in 2013. In my videos, I provide you with a three-step approach that has helped me and my students achieve excellent grades in our GCSE physics exams. The three-step process is rather straightforward. First, we tend to look at recent past papers to identify the most commonly tested questions in each chapter. Second, once we know the most commonly tested topics within each chapter, we will dive deeper into them so that we have a solid understanding of these concepts. And finally, we'll be looking at how to apply these concepts to past paper questions. So the chapters have been split as per the CAIE curriculum. However, I do want to state that if you are a student who is doing another curriculum, i.e. not CAIE, but say Edexcel, AQA or OCR, you will still benefit a lot from these videos because the concepts tested tend to overlap a fair bit, and the methodology that I will be explaining to you when solving papers will allow you to do well in your exams, irrespective of what curriculum you are in. So without further ado, let's take a look at questions from chapter 6 and 7, which are energy stores and transfers, as well as energy sources. So I have termed chapter 6 and 7 as just energy because it pertains to questions on sources, transfers, and stores. But you just have to remember that if you are following the CIA curriculum, it wouldn't be called energy, but it would be split into these two chapters. I also want to say that a lot of the concepts that are tested in chapter 8, which looks at work and power, for which I'll be making a video soon, are also closely linked to this chapter of energy. Right, with that said, I present to you here a table where I have looked at recent past papers, so questions from 2020 to 2022. I've looked at both paper 2 and paper 4, so all three variants of paper 2, as well as the three variants of paper 4. And when I had a look at these papers, I found that you get questions from trying to identify the correct energy transfer. So you'll be given different scenarios where certain types of energy transfers are happening, and you have to be able to describe the energy transfer that is taking place correctly, as well as describe efficiency. So efficiency is a concept we'll be exploring, and in efficiency, we also have to be very clear on what efficiency is and how we calculate it. So there are questions pertaining to energy efficiency calculations as well. We will see a few questions on KE, that is kinetic energy, and GPE, that is gravitational potential energy calculations, as well as being able to convert between the two types of energies. And finally, there are questions related to energy sources. So energy sources is chapter 7 of your CIA curriculum, whereas the different types of energies, the different types of energy transfers, different types of energy stores, and the calculation of efficiency sits within chapter 6, which is energy transfers and stores. So the most commonly tested concept in paper 2 is describing energy changes and describing efficiency. So we can see that 13 of 21 papers between 2020 and 2022 have had this concept tested in them. And then the second most common topic is related to energy sources. So you can see that there's not too many questions on calculations, but there will still be some questions on calculations, but the majority of questions come around describing energy transfers correctly, as well as the right energy sources. Whereas calculation related questions are a little bit more common in paper 4, especially kinetic energy and gravitational potential energy related calculations. So we can see that that's shown up in 8 of 21 papers, making it the most commonly tested concept in paper 4 for this particular chapter. I also want to mention that compared to paper 4, there are more questions in paper 2. So if you were, if you had your different papers on different days and you wanted to prioritize certain topics to prepare for paper 2, I'd say that energy is going to be a big hitter there. Whereas if you were preparing for your paper 4, I would say it could be lower down the priority list. However, I will put the disclaimer out that it is never known when a new surprise question will pop up. So it's always best to prepare all the topics and be very confident in all of the concepts and get practice and everything. However, I think what I'm trying to give you here is perhaps a smarter, more effective way of preparing, because usually the questions and the trends that you see from recent past papers is what tends to repeat itself. So with that said, if I jump into, I'll be starting off with energy sources. I'll jump into energy sources first. So energy stores and transfers. And by the way, when I'm in energy sources, I'm in energy stores, transfers, and sources. I will be covering calculation-based questions in a separate video, which I'll form as part of a series with the concepts for chapter 6 and 7. So if we look at energy stores and transfers, I've got the list of different energies here listed on the left. I have a brief description of what that source of energy is, or and essentially whether it's a store or a transfer. And I've also given here an example of where this particular type of energy is seen in action. Because again, if you remember from the list of questions we saw, a lot of questions are based around describing energy transfers correctly in different situations. So it's good to have an idea of what type of energy transfer is seen, or energy store is seen where. So if we talk about kinetic energy is the energy associated with moving bodies, and we can see that it is a store of energy. So any object that is moving, whether it has a constant speed or it's accelerating or decelerating, any kind of motion really, except when it's at rest, that body is believed to have kinetic energy. And then we have gravitational potential energy. This is the energy associated with work done against gravity. So if you were to lift an object up, you are giving it gravitational potential energy. And then when an object is dropped or an object falls from a certain height above the surface of the Earth, then it has its gravitational potential energy released. So you could see this particular type of energy in rising or falling objects. Again, it's important to keep in mind that the object gains gravitational potential energy when it's rising, and it releases gravitational potential energy when it's falling. We've next got chemical energy. So chemical energy is the energy that exists within the bonds of a substance. So it is an energy store, and any fuel or food that you will come across is a store of chemical energy. I would also say that batteries tend to have chemical energy within them. So that is again something to be wary of. Then we talk about internal energy. So this is again something that we'll be exploring in later chapters, internal energy and thermal energy. But internal energy is essentially the energy between the atoms and molecules of a substance. So a classic example where we see the internal energy change is when there is a phase change in an object. So phase change is when an object either goes from being a solid to a liquid, or liquid to a gas, or vice versa. So essentially goes in the opposite direction, gas to liquid and then liquid to solid. So when that tends to happen, a lot of energy is needed in order to give the object the amount of energy needed to go from one phase to another, or a lot of energy is released. So essentially, if you went from a solid to a liquid to a gas, you are increasing the internal energy of the particles within the substance. So you have to supply energy from external sources to enable that transformation. However, the other way around, where the object, I suppose, is cooling down from being a gas to a liquid, or from liquid to a solid, its internal energy is reducing, which means it releases a lot of energy to its surroundings or its environment. So that is internal energy. And again, I suppose the best way to visualize it is during a phase change. But again, we will be covering this in more depth in a future chapter. We've then got thermal energy, which is the energy released with the temperature of an object. So essentially, thermal energy tends to flow from hot objects to colder objects. That's why when you have a hot cup of tea, you will find that it gradually over time becomes colder, and essentially, as it loses its heat, the air around it becomes a little bit warmer. Because when you started off with just a cup of tea, which is just been boiled, you will have a very hot tea, and the air around it will be at room temperature. But then, as the tea tends to lose its heat, because it's the hotter object, it will lose its heat to the colder surroundings. The temperature of the tea falls, whereas the temperature of the surrounding air would have increased a little bit. So that is thermal energy. It can be attributed to the temperature of a body. It can also be thought of as the average kinetic energy of the particles within a substance. And an example of where it can be seen, as we've just discussed, is when an object is either heated or it's a hot object. will tend to gain thermal energy, whereas if you have a cold object, it will tend to lose thermal energy. Then you've got nuclear energy. So nuclear energy usually comes in two forms that we're aware of. One is when we have the radioactive decay of heavy unstable nuclei, so things like uranium or plutonium, breaking down into smaller, more stable nuclei. And when they tend to do that, they tend to essentially release nuclear energy. And then you've also got the fusion of light nuclei, so typically hydrogen atoms that we're aware of in the universe, which fuse together to form helium. So this is again a store of energy. And then the two ways or the examples where it's seen really is radioactive decay or during fusion. And then we've got electrical energy. A lot of our world now operates off the basis of electrical energy. I mean, we still use like fuel for a lot of cars and things like that, but essentially any energy, any energy source that's provided to a power station could be nuclear. It could be one of the fossil fuels, if you look at shortly. So all of these, are burnt so that the chemical energy within them is released, and then that is eventually converted into electrical energy, which is what is applied to our houses. So although we start off with a bit of fuel, or what we think of as conventional fuel, ultimately it all ends up in electrical energy. It's a great way of transferring energy. It's a very efficient way of doing it. So, but in a conventional sense, electrical energy is associated with moving charges, so where there's an electrical current. And then, yeah, that would be the example for that as well. If we looked at electrostatic energy, this is the energy associated with static charges. And an example of where we could see that is with charged bodies. So sometimes, if you are in a cold country and you are wearing a jumper after some time, you will sometimes feel a bit of a zap from your jumper, especially if it's a woolen jumper. And that tends to happen because it's stored up charge. And, when you wear it, it tends to release a bit of that charge, and that results in the zap feeling that you get sometimes, or I would say sometimes you get a crackling feeling as well. So that is an example of a scenario where you can experience electrostatic forces either attracting or repelling each other. Then you've got electromagnetic energy, which is the energy associated with moving electromagnetic fields. Again, this is something that we'll be looking at. So electromagnetic fields includes light. It also includes other types of electromagnetic radiation like X-rays, UV rays, which comes from the sun, X-rays, which obviously if you had an X-ray at some point in your life, you would know what an X-ray is. You also got other types like radio waves and microwaves. If you got a microwave, again, you would have experienced it at work. So these are just different forms of electromagnetic waves, and these different waves tend to have different uses. They tend to have different frequencies and wavelengths. And essentially what they are is electrical and magnetic fields oscillating perpendicular to each other. So an example of where it is seen in our day-to-day lives is with hot objects or objects that are radiating energy, so usually objects that are glowing, releasing light. They're also probably releasing other electromagnetic waves which we can't quite see with the naked eye. And you've got elastic or strain energy. So we've done a video on this chapter. So the energy associated with a deformed elastic object. So elastic objects are objects that when a deforming force is applied to it, it tends to essentially change its shape and form. But when the deforming force is removed, it returns back to its original shape and form. If it doesn't return back to its original shape and form, it's permanently deformed, which means it becomes inelastic. But the energy that is stored by these objects when they are deformed, which allows them to return back to the original state, that is elastic energy. So you've got stretch elastic objects, a classic example being springs, where it's a good case of where this type of energy is seen. And finally, you have sound energy, which is associated with material vibrations. As again, we will see in the chapter of sound. Sound is waves passing because of the vibrations in objects. So that is where you'd be able to see it as well. So that's the example, saying that it's within vibrating objects. So we can see there's a few different types of transfers. So sound energy, electromagnetic energy, electrical energy, thermal energy, all of these are different forms of transfers. You also got stores like elastic potential energy, gravitational potential energy, internal energy, nuclear energy. So those are stores, essentially. And one way I'd like to think of stores as well is anything that's a fuel or a food item or a battery or anything like that. Anything that from which other objects get energy uh, is usually a store because it has some amount of inherent energy stored in it. And as we'll see, the conservation of energy can either be created or destroyed. So if it is able to give energy to other things, it must have a store within it initially. And chemical, internal, nuclear, all of these are great sources of stored energy. So yeah, that's a quick and easy way. Either think of fuel or food or batteries. I suppose that's the quickest, easiest way. But you can also think of like the nuclei of atoms and whether they are unstable and want to like decay radioactively, or if they're light and there's a lot of energy to fuse them together. If you move on next to energy sources, again, you have loads of questions from these. Your questions usually revolve around how these energy sources release their energy, or how at least we utilize them for them to release their energy, and what are some pros and cons of these different energy sources. So the most commonly used type of energy source is fossil fuels. So this includes coal, oil, and natural gas. Again, this is formed through the decay and then the subsequent preservation of um, creatures that died millions of years ago. This could be like dinosaurs, could be like plankton, this could be trees that essentially died and fell into swamps where they could not go through aerobic decay. So essentially, fossil fuels come through those sources. So these different fuels have chemical energy within them, and generally we tend to release that chemical energy into heat and electricity. So that is how these fuels are used. So the advantages of them are they're abundant, at least at the moment in the world. We'll see that they're non-renewable, which means they're not going to be there forever. They are cheap and they're reliable. Again, they're reliable and cheap because the technology using them is very mature. We've used them for many years now. So we've managed to somehow make the price point attractive for these fuels, and we know that they have consistently delivered. However, the disadvantages, as I said, they're not going to last forever. They are fairly abundant now, but they're not going to last forever. And um, there is a lot of concern around global warming and climate change, and fossil fuels have been a major contributor for that. And they also release other types of pollutants into the atmosphere, like nitrous oxides and sulfur dioxide and carbon monoxide, all of which are poisonous to humans and other creatures on the planet. The next one is biomass. So biomass tends to convert chemical energy from plant and animal waste into heat and electricity. So it works in a very similar way to fossil fuels, but it uses sort of the waste of plant and animals to be able to do that. The pros are it's renewable, it's reliable, it's cheap. The cons are usually it's used to provide heat in lowly developed countries, and usually when it's burned, it's not very well ventilated, and that tends to release uh, particulate matter. It tends to release carbon monoxide, and all of these things can cause health issues for the people relying on biomass to provide them with heat. You have solar energy. Solar energy is essentially the conversion of the sun's light into electricity using photovoltaic cells. Very smart technology. The pros are that it's renewable because as long as the Earth is around, the sun will be around. Once the sun's not around, the Earth's not going to be around. So it is renewable. It is cheap. It wasn't always the case, but over the last decade or so, the price point has come lower and lower thanks to contributions from industry and the scientific community, and it's also safe. But the cons are it's unreliable. It depends on solar intensity. So in countries like the UK, which is a classic example, the business case for it is not that great. And also in all parts of the world, when it's night time, you are not going to be able to make any electricity. And it also typically requires a large area to be able to realize um, a viable amount of electricity or energy from solar. If we look at wind, wind tends to convert the kinetic energy of wind currents into electricity. So essentially, a windmill, its blades are turbine blades. The turbine blades are connected to a generator, and the generator converts the movement of the blades into electricity. So this is how most turbines work. So whether it's with fossil fuels, whether it's with plants that tend to use biomass, whether it's with hydroelectricity, so all types of power plants tend to have some mechanism of making a turbine turn, and the turning turbine is connected to a coil, and the coil rotates in a way where, because of the rotation of the coil, it induces an electric current, and this induced electric current is how we can convert energy from these different sources into electricity. Obviously, the way it's done is different for different sources. For hydroelectricity, it's about water hitting a turbine blade. For wind, it's just the wind directly brushing against the blades. For fossil fuels and biomass, usually the heat from these fuels is used to essentially it heats up water in a boiler, and the water is converted to steam, and the steam is then forced against the blades of a turbine. So in all of these cases, there's different ways in which we get from the source to a rotating turbine to a rotating coil and then electricity. So that's essentially what happens. The pros for wind energy is the fact that it's renewable, it's cheap, and it's safe. The cons is it's unreliable. It's not windy every day, as we all know, and it can also be noisy. One of the complaints is that, especially when you're closer to the windmills, it creates a lot of noise. There's also been complaints about areas of windmills not necessarily looking very pretty. So I suppose that's a smaller or a smaller con, or rather an inconvenience more than anything else. But I'd say the big sort of hitters are the fact that it's unreliable and it can be noisy. When we look at waves, waves tend to convert the kinetic energy of waves into electricity. So again, a similar mechanism to windmills, but this time using waves. The pros are it's renewable, and the cons are it's unreliable. Again, the wave height needs to be at a certain level in order to be able to get any significant amount of electricity out, and it's costly for maintenance. So it's not quite as cheap as windmills, which are, I suppose, a more proven technology in the space. So hydroelectricity, it converts potential energy of stored water, which is in a reservoir or a dam, and then that water falls onto a turbine blade. The blade rotates, and then the turbine is connected to a coil, which rotates, and it induces a current. So essentially, that is how it works. The pros are it's renewable, it's safe. The cons are that there's going to be flooding risks. This tends to happen, especially in areas near a dam, and it's also costly to construct. Again, when it comes to costs for all of these different types of technologies, there's the cost of um, installing these technologies, and there's the cost of maintaining them. So as we can see for wave energy, um, it's costly to maintain the system, whereas for hydroelectricity, it's very expensive and time consuming to build the dam. So those are the disadvantages of that. Again, for all of these different sources, you would be expected to remember one or two pros and one or two cons. So you're not going to have to know more than that. So it's important for you to. I've just given a couple here in most cases, so it's just something to keep in mind in case you get tested on it. So tidal energy is the next one, where it converts the potential energy of waves into electricity. So this is slightly different from wave energy. In tidal energy, it's about essentially the height of the tide, and the height of the tide varies with the day and night cycles that different regions have. So pros are it's a renewable, reliable, and safe form of electricity generation, and the cons are flooding risks. So quite similar to hydroelectric that way. Geothermal energy, it converts the thermal energy from rocks that are underneath the surface of the earth into electricity. Essentially, you have geysers and things like that, and you could use the I suppose the pressure of the water as well as the steam to be able to turn a turbine. So the pros are it's clean, the cons are it's unreliable and scarce. There's not many regions in the world which have these hot rocks underneath their surface. Iceland is a great example, but it's not very common in a lot of countries. And then finally, you've got nuclear energy, which converts the nuclear energy from radioactive decay of unstable nuclei into electricity. We still can't do nuclear fusion on Earth. Obviously, on the Sun, you have the fusion of two light nuclei to be able to release a lot of energy. We can't yet have a sustainable, fully controlled nuclear fusion reaction on Earth. But at the moment, the nuclear power stations that we see around rely on the decay of unstable nuclei. So that is how we produce our nuclear energy. The pros are it's clean and it's a highly concentrated source of energy, much more so even than fossil fuels. I think what you can produce with a single truckload of nuclear fuel will require a train load of fossil fuels. So you can do a lot more with nuclear energy because it's a very concentrated form of energy. But the cons are it's scarce, it's non-renewable, and there's always safety concerns and risks, especially after disasters like Fukushima and Chernobyl. There's obviously concerns. It is generally a very safe form of electricity creation and generation, but there are underlying concerns because of these industry disasters that have occurred. And then the other type of questions you get for energy sources, apart from stating what energy transfer or transformation they tend to use, as well as being able to state a pro and a con to each of them, I think the other questions are around whether they're renewable, whether they're clean, and whether they rely on the sun. So for fossil fuels, they're definitely not renewable, which means that they are not going to last forever. They will run out at some point. Are they linked to the sun? Indirectly, yes, because the energy stored in fossil fuels is essentially from creatures that died, chemical energy of creatures that died millions of years ago. Sorry, and these creatures used to rely on the sun, whether it was the plants, whether it was the plankton. All of them tend to rely on the sun for their source of energy, or the animals as well. They used to eat the plants that relied on the source of energy. So yes, indirectly it is linked to the sun. Biomass is renewable. And it says, yes, it is also indirectly linked to the sun. Living beings rely on the sun to make food and produce waste. And is it a clean form of energy? Yes, but it's important to realize that it's not a net emitter. So if you use plant waste, for example, and you're going to burn plant waste, you will release some carbon dioxide. But because the plant over the source of its life tends to absorb a lot of carbon dioxide to make food through the process of photosynthesis, we could say that on the whole, biomass is a cleaner source of energy than fossil fuels. Then solar, it's renewable. Yes, as long as the sun is there, we'll have solar. It's linked directly to the sun, and it is a clean source of energy. Wind, yes, it's a renewable form of energy. It's again, we will, as long as the Earth is round, we will have wind and we will have waves. They're both similar like that because it's because of the air currents that we have. If the air currents are over land, we can capitalize that as onshore wind. If the air currents are in the sea, we can capitalize that as both wave energy and offshore wind. So as long as there's winds on the planet, we will be able to generate electricity using those sources. So they are renewable. Where they're linked to the sun, wind is directly linked to the sun because wind patterns are governed by the different levels of heating in different areas of the earth, and waves as well because they rely on winds too. It's a similar logic for them, and they're both clean forms of energy. If you look at hydroelectric is renewable as well because, again, as long as we have these different rivers and they are being actively fed by glaciers, we will have these active sources of water that we can create as reservoirs and then capitalize into hydroelectric energy. Is it linked to the sun? It's not linked to the sun. And is it clean? It is absolutely clean. There are no, and again, it's important to remember that when we say clean, we're talking about carbon dioxide, carbon monoxide, nitrous oxide, sulfur dioxide emissions. For most of the sources that we see here, we will not be having these emissions, whereas with fossil fuels, we do have these emissions. That's why they're not clean. So then if we move on to tidal is also renewable, as long as we have oceans and estuaries and things like that. And as long as the moon is there, we will have tidal, essentially tidal effects, and that means we can capitalize on tidal energy. It's not linked to the sun; it's linked to the moon. In fact, I've seen questions in past papers which ask you for source of energy that's not linked to the sun. Tidal is an easy choice. And then, is it clean? It is a clean source of energy. If you look at geothermal vents, that is also a renewable source of energy. It's not linked to the sun because it is about hot rocks under the surface of the earth, so they probably don't see the sun at all, and it's a clean source of energy. And finally, we've got nuclear energy, which is not renewable because we've seen quite a few force sources that are renewable. But nuclear energy, like fossil fuels, is limited because fossil fuels, we need to have oil deposits, natural gas deposits, coal deposits. For nuclear fuel, you will need deposits of uranium, thorium, a few different radioactive substances that you can use, and obviously they have limited reserves in the planet. So it is non-renewable. Is it linked to the sun? It's not linked to the sun. It's linked to radioactive decay of substances. Is it clean? Yes, it is a clean source of energy. So essentially, this is the theoretical aspect of chapters 6 and 7. To be able to describe what an energy store is, what an energy transfer is, what it's associated with, and to be able to give examples of it, to be able to describe different energy sources and the energy transformations they rely on, what are the pros and cons of using these different sources of energy, as well as whether they're renewable, whether they are directly or indirectly linked to the sun, and whether they're clean, right? So these are the questions that relate to describing energy transformations that are linked to describing energy sources. We can see that you get a lot of these questions in your paper twos. So I hope that the tables, feel free to take a screenshot of them, and I hope that these tables summarize the information given in these two chapters regarding energy sources, transfers, and stores for you when you prepare for the exam. So I'll be creating another video where we will look at calculations for kinetic and potential energy, i.e. gravitational potential energy, as well as efficiency calculations. And I will link this video to that video so that you have continuity as part of the series for chapter 6 and 7. I will join you in that video. Thank you.